Hello everyone, I'm Shazil, and today we are going to take a deep dive into gRPC, which is Google's high performance open source RPC framework. It is used as an alternative to standard REST frameworks in modern distributed systems. Before we really get into what gRPC actually is, we have to answer a couple of questions. For example, what problem does gRPC solve? Or why are big companies shifting their internal service communication to gRPC? The following section lays the foundation for that. The traditional REST APIs using JSON and HTTP 1.1 have a few limitations. For example, JSON is text-based, which makes it large and slow for machines to parse. HTTP 1.1 suffers from head-of-line blocking, which increases its latency, and REST follows a rigid request-response model, meaning real-time streaming is difficult. These constraints become painful as systems scale and require low latency. To solve all these problems, this is where gRPC comes in. gRPC uses a schema-first approach with protocol buffers, allowing a client to call remote methods as if they were local. It runs on HTTP2, giving significant performance improvements and enabling modern communication patterns like streaming. Let's compare the modern gRPC and the traditional REST framework. Here's a simple comparison. gRPC uses binary protobufs which are smaller and faster than JSON. gRPC uses HTTP2 instead of HTTP 1.1. It enforces a strict .proto contract, improving the reliability, and it provides native streaming. Meanwhile, REST is text-based, loosely structured, and not built for real-time communication. Now that we know the why, let's go deeper into the how. What makes gRPC so fast, reliable, and efficient? There are three core technologies that make it possible. On the top of the list, we have protocol buffers. You define your data in a .proto file. The data is then serialized as a compact binary file, and then the Proto-C compiler generates client and server code in multiple languages. This makes development extremely fast and consistent. Next, we have HTTP2. HTTP2 supports multiplexing, which means multiple requests over a single connection. The HTTP2 header compression really saves bandwidth, and the server push enables better responsiveness. HTTP2 is a major reason gRPC performs better than REST framework. The last core technology we have are the four types of streaming that gRDP offers. First of all, we have unary RPC, which is the classic request response, just like the REST framework. Then we have server streaming, where clients send one message and server stream back many messages. Along with that, we have client streaming, where client streams many messages and server sends only one back. For example, when client is uploading a large file. There's also bidirectional streaming, where both client and server stream messages independently. For example, a real-time chat service. As we can see in the benchmark result here, gRPC was able to send around 900k messages per second, whereas REST API was only able to send 300k messages per second. This is because of binary serialization and HTTP2 transport of gRPC protocol. There are three important runtime concepts in gRPC. First, we have a channel, which manages the HTTP2 connection between a client and a server. Next up, we have a stub, which is an auto-generated client object. It translates our local function calls into a remote RPC call. And at last, we have a deadline, which prevents long-running or stuck RPC calls. If in any case it's exceeded, the call is terminated with an exception deadline exceeded. Now let's talk about how we plan to adopt gRPC internally in our systems. gRPC is the perfect fit for microservices communication. We can also use gRDP in real-time applications, for example, for live updates, notifications, or IRE data ingestion. We can also use gRDP in mobile clients, which exponentially increases the mobile app performance. At last, we have polyglot systems, which basically connects our Python applications, Go, Java, and even more. All of these are relevant to our architecture. Let us discuss the few main components of gRPC ecosystem. gRPC is a CNCF project, which is part of the Cloud Native Computing Foundation, just like Kubernetes. gRPC Web allows browser clients to talk to gRPC services via proxy, bringing gRPC benefits to the front end. gRPC Gateway auto-generates REST endpoints from gRPC services. This whole ecosystem makes adoption easier. Now let's walk through a real example of gRPC practical implementation where we'll be defining a contract, we'll be generating code, implementing the server logic, and also making a client call. In the first step, we define a contract in .protofile, which is a single source of truth. The .protofile is actually language agnostic. If we write it once, we can export it in many different languages, for example, Python, Java, Go, Node, etc. It is strongly typed, which means it clearly defines service methods and message structures. Once the .proto contract is ready, we run the proto-C compiler. It automatically generates the server base classes and the client stubs. We don't need any boilerplate or manual parsing, and everything is handled for us. Next is server developers simply subclasses the generated servicer and write business logic. They don't worry about JSON parsing, routing, or any type of headers. They just simply focus on our core application logic. Finally, the client uses the generated stub to call the remote service like a normal function. gRPC abstracts away the networking, making it feel local even though it's remote. To summarize our whole discussions in a few words, we can say that gRPC is faster than standard REST framework using protobufs and HTTP2 protocol. gRPC is stricter thanks to the schema first contracts. It is more flexible due to the four streaming patterns, and we are starting gRPC with a pilot to adopt it smoothly. If you have any questions regarding this presentation or gRPC in general, please feel free to ask. Thank you so much for your attention.